The asteroid belt represents one of the most fascinating regions in our solar system, serving as a dividing line between the inner rocky planets and the outer gas giants. Located between Mars and Jupiter, this disc-shaped band of celestial objects holds clues to the formation and evolution of our planetary neighborhood. The belt consists of millions of asteroids ranging from tiny pebbles to dwarf planets, collectively telling the story of a planet that never formed. While often portrayed in science fiction as a densely packed region where spacecraft must navigate treacherous obstacles, the reality is quite different. The vast majority of the belt is empty space, with considerable distances between individual asteroids. This comprehensive examination explores the asteroid belt's physical characteristics, formation history, composition, dynamic processes, and its significance within our solar system. The asteroid belt occupies a well-defined region of space in our solar system, situated between the orbits of Mars and Jupiter. This positioning has profound implications for its structure and evolution, creating a unique cosmic environment unlike any other in our planetary neighborhood. The asteroid belt is located approximately 2.2 to 3.2 astronomical units, AU, from the Sun, with 1 AU representing the average distance between Earth and the Sun. This places the belt at a significant distance from our planet, spanning a region approximately 140 million miles across. The belt forms a torus-shaped or disc-shaped region centered on the Sun, following roughly the same plane as the planet's orbits. This distinctive formation is often referred to as the main belt, to distinguish it from other asteroid populations in the solar system, such as the Lagrangians and Centaurs. The structure of the belt is not uniform, but features varying densities of objects throughout its volume, with some regions being more populated than others due to gravitational influences and resonances. Within the asteroid belt, objects are organized into 8 recognized subgroups, each named after a significant asteroid within that collection: the Hungarias, Floras, Phocaea, Coronis, Eos, Themis, Cybele, and Hildas. These groupings help astronomers categorize and understand the complex distribution of objects within the belt. Despite containing billions of asteroids, these objects are spread across an immense volume of space, with an average distance between asteroids of approximately 965,600 kilometers, 600,000 miles. This vast separation explains why spacecraft have successfully traversed the asteroid belt without incident, including NASA's New Horizons mission to Pluto. The distribution of asteroids is also influenced by orbital resonances with Jupiter, creating gaps similar to the Kirkwood gaps where few asteroids exist due to gravitational perturbations. The asteroid belt contains objects of remarkably diverse sizes, from microscopic dust particles to the dwarf planet Ceres. While hundreds of thousands of asteroids are currently catalogued, the total number ranges in the millions or more, depending on the minimum size considered. Survey data indicates that over 200 asteroids are larger than 100 kilometers in diameter, and between 700,000 and 1.7 million asteroids have diameters of at least 1 kilometer. The number of asteroids steadily increases with decreasing size. Though interestingly, researchers have identified bumps in the size distribution curve at approximately 5 kilometers and 100 kilometers, where more asteroids than expected are found. Most asteroids larger than about 120 kilometers in diameter are considered primordial, having survived intact since the solar system's formation, while smaller asteroids are typically fragments resulting from collisions. The absolute magnitudes of most known asteroids fall between 11 and 19, with a median of about 16, providing insight into their reflectivity and surface properties. The asteroid belt represents a fossil record of our solar system's formation, preserving evidence of processes that occurred billions of years ago. Its current state reflects a complex evolutionary history involving planetary formation, migration, and gravitational interactions. The story of the asteroid belt began approximately 4.6 billion years ago during the formation of our solar system from a rotating disk of gas and dust. Within this protoplanetary disk, solid materials began to clump together through a process called accretion, forming numerous planetesimals, rocky bodies ranging from several kilometers to hundreds of kilometers in diameter. Initially, these planetesimals followed circular coplanar orbits, and began to merge to create larger protoplanets throughout the solar system. Evidence suggests that the asteroid belt formed remarkably quickly within the first 10 million years of the solar system's existence, as indicated by studies of zircon crystals in meteorites believed to originate from the asteroid Vesta. During their early history, the larger asteroids experienced significant heating, causing partial melting that allowed elements within them to differentiate by mass. Heavier elements sank toward the center while lighter materials rose to the surface. Some progenitor bodies may even have undergone periods of explosive volcanism and formed magma oceans, though this melting period was necessarily brief compared to the much larger planets and had generally ended about 4.5 billion years ago. The most critical factor in the asteroid belt's development was the formation and gravitational influence of Jupiter, the solar system's largest planet. As Jupiter formed beyond the snow line where water existed as ice, it grew rapidly to become a massive gas giant. Jupiter's substantial gravitational field strongly perturbed the orbits of planetesimals in what would become the asteroid belt, creating orbital resonances where the orbital period of an object formed an integer fraction of Jupiter's orbital period. As Jupiter potentially migrated inward following its formation, these resonances swept across the asteroid belt, dynamically exciting the region's population and significantly increasing the relative velocities between objects. These higher velocities had a profound consequence. In regions where collision speeds were too high, the shattering of planetesimals dominated over accretion, preventing the formation of a planet. Instead of continuing to grow into a full-size planet, the material in this region remained as separate bodies orbiting the Sun, occasionally colliding and fragmenting further. This explains why the asteroid belt contains far less material than would be expected for a planetary formation zone. Jupiter effectively stunted the growth of what might have become the solar system's fifth rocky planet. The current asteroid belt represents only a small fraction of its original mass and population. Scientists estimate that the primordial population of the main belt was approximately 200 times more massive than what exists today. This dramatic mass depletion could not have occurred through collisional erosion alone. The integrated collisional activity of the asteroid belt is equivalent to what would be produced at the current collision rate over 8 to 10 billion years. This suggests that the mass depletion occurred very early in the solar system's history, and almost certainly coincided with the dynamical excitation event that stirred up eccentricities and inclinations. The early asteroids likely had nearly circular orbits with low inclinations, but today they occupy orbits with eccentricities ranging from near circular to highly elliptical and inclinations between 0 degree and 33 degrees. This scattered distribution of orbital parameters indicates that powerful dynamical processes reshaped the belt soon after its formation. Interactions with Jupiter, and perhaps other migrating planets, scattered many asteroids into unstable orbits, ejecting them from the belt entirely or sending them crashing into the Sun or planets. After this intense period of depletion and reorganization, the asteroid belt settled into a configuration more similar to what we observe today. The asteroids within the belt exhibit remarkable diversity in their composition, reflecting differences in their formation conditions and subsequent evolution. Understanding these variations provides crucial insights into the thermal and chemical gradients that existed in the early solar system. Asteroids are categorized into several taxonomic classes based on their spectroscopic signatures in visual and infrared wavelengths. The three primary classifications are C-type, S-type, and M-type asteroids, each with distinct compositions and physical properties. C-type, carbonaceous asteroids are the most common, comprising approximately 75% of known asteroids. These dark-colored objects contain significant amounts of carbon and volatile compounds, representing some of the most primitive material in the solar system. S-type, silicaceous asteroids are the second most common group, composed primarily of silicate rock and some metallic nickel iron. Their composition is similar to many stony meteorites that reach Earth. M-type, metallic asteroids, consist mainly of nickel iron and represent cores of larger differentiated bodies that were shattered through collisions. This diversity in composition does not follow a strict radial pattern with distance from the Sun, as one might expect from temperature gradients in the protoplanetary disk. Instead, different classes are partially mixed throughout the belt. This mixing suggests significant orbital migration and scattering events during the early solar system, potentially caused by the gravitational influence of forming and migrating giant planets. The four largest objects in the asteroid belt, Ceres, Vesta, Pallas, and Hygiea, contain approximately 62% of the belt's total mass, with Ceres alone accounting for 39%. Ceres stands apart as the only asteroid officially classified as a dwarf planet, with a diameter of about 940 kilometers, making it the largest object in the inner solar system that isn't a major planet. Vesta, the second largest asteroid at about 525 kilometers in diameter, has a unique history evidenced by its basaltic crust, a sign it once had sufficient internal heat for volcanic activity and differentiation into layers. Pallas, with a diameter of approximately 512 kilometers, has an unusually high orbital inclination compared to most main belt objects. Hygiea, the fourth largest at roughly 430 kilometers across, is a dark, primitive body that appears to be the largest member of a prominent asteroid family, likely formed from a catastrophic impact. These massive bodies survived the violent early history of the solar system relatively intact, making them crucial targets for scientific study. The Dawn mission, which visited both Vesta and Ceres, revealed these bodies to be complex worlds with unique surface features, compositions, and geological histories, rather than simple chunks of rock and metal. The physical structure of asteroids varies considerably based on their size, composition, and collision history. Many asteroids larger than 120 kilometers have remained relatively intact since the solar system's formation, and often show evidence of differentiation, with heavier elements concentrated toward their centers. In contrast, most main belt asteroids between 200 meters and 10 kilometers in diameter are believed to be rubble piles, loose collections of fragments held together primarily by self-gravity rather than material strength. These bodies form through the reaccumulation of debris following catastrophic collisions and contain significant amounts of internal porosity. Smaller asteroids typically represent fragments from larger parent bodies, while the smallest particles form a complex dust population. The surfaces of asteroids bear witness to their violent collisional history, with most showing heavy cratering and irregular shapes. Impact events have shaped not only individual asteroids, but entire families of objects sharing similar orbital characteristics and compositions, representing the fragments of once larger parent bodies. Spectroscopic studies reveal a wide range of surface compositions, from primitive carbonaceous materials to processed igneous rocks, providing a window into the thermal and chemical conditions present during the early solar system. Far from being a static collection of rocks, the asteroid belt is an active environment characterized by ongoing collisions, dust production, and complex orbital dynamics. These processes continue to shape the belt's structure and connect it to other regions of the solar system. The asteroid belt exists in a state of slow but continuous evolution, driven primarily by collisions between its members. Impact events between main belt bodies with a mean radius of 10 kilometers are expected to occur approximately once every 10 million years, though smaller collisions happen much more frequently. These impacts produce a range of outcomes depending on the relative velocities and sizes of the objects involved. High-speed collisions typically result in fragmentation, creating new asteroid families that share similar orbital elements, but gradually disperse over time due to gravitational and non-gravitational forces. Conversely, low-velocity collisions may result in the joining of two asteroids into a single larger body. After more than 4 billion years of such processes, the current members of the asteroid belt bear little resemblance to the original population, with most smaller asteroids being fragments rather than primordial objects. Mathematical models suggest that the integrated collisional activity experienced by the asteroid belt is equivalent to what would be produced at the current collision rate over a period of 8 to 10 billion years, indicating that the most intense period of collisional evolution occurred early in the solar system's history, when the belt was more densely populated. The asteroid belt serves as a significant source of dust in the inner solar system through multiple mechanisms. Collisions between asteroids produce fine particulate matter with radii up to a few hundred micrometers, while micrometeorite impacts on asteroid surfaces continually generate additional dust. This fine material does not remain stationary, but undergoes a gradual migration inward toward the Sun due to the Poynting-Robertson effect, whereby the pressure of solar radiation causes small particles to lose angular momentum and spiral inward. Asteroid dust, combined with material ejected from comets, contributes to the zodiacal light, a faint glowing band visible from Earth along the ecliptic plane shortly after sunset or before sunrise. Asteroid particles that produce visible zodiacal light average about 40 micrometers in radius and typically have lifetimes of approximately 700,000 years before being destroyed or removed from the inner solar system. To maintain the observed dust bands, new particles must be steadily produced within the asteroid belt. Interestingly, computer simulations have attributed approximately 85% of zodiacal light dust to fragmentations of Jupiter family comets rather than asteroid collisions, with asteroids contributing at most 10% of the observed dust. This finding highlights the complex interrelationships between different populations of small bodies in the solar system. Orbital resonances play a crucial role in the long-term dynamics of the asteroid belt, creating both stability zones and regions of instability, where asteroids cannot persist for long periods. These resonances occur when the orbital period of an asteroid forms a simple integer ratio with that of Jupiter or other planets, resulting in regular gravitational perturbations that can either stabilize or destabilize orbits. Mean motion resonances with Jupiter create noticeable gaps in the distribution of asteroids, similar to the Kirkwood gaps in Saturn's rings, where few objects can maintain stable orbits. Secular resonances, which involve synchronicity between the precession rates of orbits, can gradually increase the eccentricity and inclination of asteroid orbits until they cross the path of a planet, leading to potential ejection from the belt or collision with a planet. These dynamic processes continue to sculpt the asteroid belt, causing a slow but steady loss of material over billions of years. Additionally, non-gravitational forces such as the Yarkovsky effect, a thermal force resulting from the uneven heating and cooling of rotating asteroids, can cause small objects to drift in semi-major axis over time, eventually pushing them into resonances that may remove them from the belt. The combination of these mechanisms ensures that the asteroid belt remains a dynamically active region, with individual objects continuously evolving in orbital space. The asteroid belt does not exist in isolation, but maintains important connections with other parts of the solar system, including Earth. One of the most direct connections between the asteroid belt and Earth comes in the form of meteorites, fragments of asteroids that survive passage through Earth's atmosphere and reach the surface. Of the approximately 50,000 meteorites found on Earth to date, scientists believe that 99.8% originated in the asteroid belt. These meteorites provide invaluable samples of asteroid material that can be studied in laboratories, offering insights into the composition, age, and thermal history of their parent bodies without the need for costly sample return missions. Meteorites originate when collisions in the asteroid belt create fragments that are gradually pushed into unstable resonances by forces such as the Yarkovsky effect, eventually finding their way into Earth-crossing orbits. The delivery of asteroid material to Earth is not limited to the present day. Throughout Earth's history, asteroid impacts have played significant roles in shaping our planet's geology, atmosphere, and even biological evolution. The most famous example is the Chicxulub impact approximately 66 million years ago, which contributed to the extinction of non-avian dinosaurs and allowed mammals to diversify. While catastrophic impacts are rare in the current era, smaller asteroid fragments regularly enter Earth's atmosphere as meteors, with some reaching the surface as meteorites. The asteroid belt has been an object of scientific interest since the discovery of Ceres by Giuseppe Piazzi in 1801, marking the first recognized asteroid. Since then, ground-based telescopes, space observatories, and direct spacecraft missions have dramatically expanded our knowledge of these objects. Telescopic surveys have cataloged hundreds of thousands of asteroids, determining their orbits, approximate sizes, and in many cases their spectral classifications. Space-based missions have provided more detailed information through close-up observations and even landings on selected targets. NASA's Dawn mission, which orbited both Vesta and Ceres between 2011 and 2018, revealed these large asteroids to be complex worlds with unique geological features and histories. The Japanese Hayabusa mission successfully returned samples from asteroids Itokawa and Ryugu, while NASA's OSIRIS-REx mission collected samples from asteroid Bennu for return to Earth. These direct examinations have transformed our understanding of asteroids from distant points of light to geologically diverse worlds with their own evolutionary histories. Despite the vast number of asteroids in the belt, the enormous distances between them mean that spacecraft can safely pass through the region without significant risk of collision, as demonstrated by numerous missions to the outer solar system. The asteroid belt serves as a preserved record of the solar system's formative processes, offering valuable insights that help scientists reconstruct our cosmic neighborhood's early history. Unlike the planets, which have undergone substantial geological evolution, erasing much of their primordial characteristics, many asteroids, especially the larger ones, have remained relatively unchanged since their formation. The partial mixing of taxonomic classes throughout the belt, rather than a neat radial arrangement by composition, provides evidence for significant dynamical restructuring of the early solar system, possibly involving the migration of giant planets. The compositional diversity of asteroids reflects the temperature and chemical gradients that existed in the protoplanetary disk, with more volatile-rich objects generally forming at greater distances from the Sun. The snow line, the distance from the Sun beyond which water could exist as ice rather than vapor, appears to have played a crucial role in asteroid belt evolution, with evidence suggesting that many asteroid belts form near this boundary in stellar systems. By studying the current structure, composition, and dynamics of the asteroid belt, scientists can test and refine models of solar system formation and evolution, constraining theories about the sequence and timing of key events in our planetary system's development. Beyond its astronomical importance, the asteroid belt may have played crucial roles in the development of life on Earth and potentially on other worlds. Its influence extends from the delivery of essential materials to the ongoing protection and stability of habitable planets. Asteroids likely served as significant vectors for delivering water and organic compounds to the early Earth, materials essential for the emergence of life as we know it. During the early bombardment phase of Earth's history, impacts from water-rich carbonaceous asteroids may have contributed substantially to our planet's water inventory, supplementing or even providing the majority of Earth's oceans. This delivery occurred through the gravitational scattering of asteroid belt objects into Earth-crossing orbits, a process facilitated by resonances with Jupiter and other planets. In addition to water, asteroids transported organic compounds, including amino acids and nucleobases, the building blocks of proteins and DNA, which have been identified in carbonaceous meteorites originating from the asteroid belt. These prebiotic compounds could have jump-started chemical evolution on the early Earth, providing ready-made ingredients for life's emergence rather than requiring their formation from scratch in Earth's primitive atmosphere. The asteroid belt's position near the snow line of the solar system made it a particularly important reservoir for water and volatiles, as objects that formed beyond this boundary incorporated significant amounts of ice into their structures. Earth's habitability thus appears intimately connected to the existence and evolution of the asteroid belt, highlighting the interconnected nature of our planetary system. The relationship between the asteroid belt and terrestrial planets includes both hazardous and protective aspects regarding impacts. While asteroids diverted from the belt have caused significant impact events throughout Earth's history, the current rate of major impacts is relatively low compared to the early solar system. The presence of Jupiter serves a dual role in this dynamic. While its gravity can divert some asteroids into Earth-crossing orbits, it also acts as a gravitational shield, capturing or ejecting many potential impactors that might otherwise threaten inner planets. This protective function may be essential for the long-term stability of biospheres on terrestrial planets, preventing extinction-level impact events from occurring too frequently for complex life to evolve and diversify. The delivery of impacts at a moderate rate might even benefit biological evolution by occasionally disrupting ecosystems and creating new evolutionary opportunities without completely sterilizing the planet. Some astrobiologists propose that the specific architecture of our solar system, including the position and nature of the asteroid belt and its relationship with Jupiter, might be unusually favorable for the evolution of complex life. a consideration relevant to the search for habitable exoplanets. The asteroid belt represents a vast repository of resources that could prove valuable for future space exploration and development. Many asteroids contain significant concentrations of metals, including precious and industrial metals like platinum, gold, and iron, often in forms more accessible than in Earth's crust, where these elements have largely sunk toward the core. Water-rich asteroids could serve as sources of fuel and life support for deep space missions, with water potentially being split into hydrogen and oxygen for rocket propellant, or used directly for radiation shielding and life support. The low gravity of asteroids makes them energetically favorable targets for resource extraction compared to planetary bodies, as materials can be removed without overcoming strong gravitational fields. Several companies and space agencies have begun developing technologies for asteroid resource utilization, though significant technical and economic challenges remain. Beyond practical applications, continued scientific exploration of the asteroid belt promises further insights into solar system formation, the origins of life, and the processes that render planets habitable. Future missions targeting diverse asteroid types across the belt would provide a more complete picture of this complex region and its role in shaping our cosmic environment. The asteroid belt stands as a fascinating cosmic frontier that has played multiple crucial roles in the development and current state of our solar system. Far from being merely a collection of failed planetary material, it represents a dynamic, evolving system that connects the inner and outer solar system through complex gravitational interactions and the exchange of material. Its formation and evolution were profoundly shaped by Jupiter's gravitational influence, which prevented the region's planetesimals from accreting into a single planet and instead created the scattered belt of objects we observe today. This process appears tied to the location of the snowline in the early solar system, suggesting that similar belts might be common features in other planetary systems. The asteroid belt serves as an invaluable scientific resource, preserving relatively pristine material from the early solar system that provides crucial insights into the conditions and processes of planetary formation. The diversity of asteroid compositions reflects the thermal and chemical gradients of the protoplanetary disk, while their current distribution reveals the dynamic reshuffling that occurred during the solar system's formative period. Through the delivery of meteorites, the belt continues to provide scientists with physical samples of these ancient materials for detailed laboratory analysis. Beyond its scientific significance, the asteroid belt has likely played vital roles in Earth's habitability and the evolution of life. The delivery of water, organic compounds, and heavy elements through asteroid impacts may have been essential prerequisites for life's emergence on our planet. The belt's ongoing interactions with Jupiter help regulate the rate of impacts on Earth, potentially providing a balance between too many catastrophic collisions and too few evolutionary drivers. As humanity looks toward the future of space exploration and development, the vast resources contained within asteroids may prove invaluable for sustaining a permanent human presence beyond Earth. In essence, the asteroid belt is not merely a leftover region of scattered rocks, but a dynamic, integral component of our solar system with far-reaching implications for planetary science, astrobiology, and the future of space exploration. Its study continues to yield important insights into our cosmic origins and may hold keys to humanity's expansion into the solar system.